when a neural network layer produces an output during training, if the prediction is wrong, a signal called a gradient flows backward through the layers, telling each one how to adjust. But researchers realized years ago that forcing gradients through every single layer causes problems. They can either vanish or explode. The solution? Residual connections. When they were introduced, they didn't just improve models, they practically saved deep learning. Before residuals, training deep networks was fragile. Stacking more layers eventually made learning slower. Gradients disappeared, and performance actually got worse. Residual connections changed all that. They provided a stable shortcut, letting information flow forward and backward without distortion. Suddenly, very deep networks became trainable. Because residuals worked so reliably, they stopped being seen as a design choice and became infrastructure. Model developers focused on bigger parameters, better attention mechanisms, and more data, while the internal flow between layers stayed mostly untouched. Residuals were predictable and stable, but they came with a subtle trade-off. Stability limited flexibility. All information had to flow through a single narrow path. For a while, that wasn't an issue. Bigger models kept improving, but eventually, as reasoning tasks became harder, that narrow pathway became a bottleneck. This is where hyperconnections come in. Instead of passing a single stream of information, why not multiple streams? More streams mean more capacity, more ways to combine information, and better multi-step reasoning. Initially, training looks fine. Loss decreases, metrics improve. But as depth increases, the unconstrained streams interact unpredictably. Gradients amplify layer after layer, lost spikes. And training can collapse suddenly, sometimes after 10,000 steps. That unpredictability makes hyperconnections risky for large-scale models. Enter DeepSeek with their breakthrough Manifold Constrained Hyperconnections MHC. The idea is simple. Allow multiple streams to communicate, but constrain the total signal strength. Using strict mathematical rules, every row and column of the mixing matrices sums to 1. They ensure information can mix, but cannot explode or vanish. The Sinkhorn-Knopp algorithm projects these matrices onto the Birkhoff polytope, guaranteeing stability across all layers. With MHC, models keep the stability of residual connections while gaining the flexibility of multiple streams. This allows for wider internal data flow without risking collapse. And the results speak for themselves. DeepSeek trained language models with 3B, 9B, and 27B parameters and across multiple benchmarks. MHC consistently outperformed standard hyperconnections, especially on reasoning-heavy tasks. This isn't just theory. They engineered the training stack for efficiency, writing custom GPU kernels using selective recomputation and overlapping communication with computation. The outcome, a 400% increase in internal capacity with only about a 6 to 7% increase in training time. The implications are huge. MHC, demonstrates that rethinking information flow inside a model can be more impactful than just stacking layers or adding parameters. It opens new directions for large-scale AI design while maintaining stability. DeepSeek's work also signals a strategic shift. They openly publish foundational ideas, encouraging experimentation while maintaining a competitive edge. Analysts are already watching closely, anticipating that MHC concepts may power the next generation of DeepSeek models. If widening information flow inside a model can yield bigger gains than simply adding layers, what other accepted solutions in AI might be hiding untapped potential? If you found this breakdown helpful, hit like, subscribe, and stay tuned for more deep dives. See you in the next one.